The Existential Crisis Hotline. The Existential Crisis Hotline. The Existential Crisis Hotline. The Existential Crisis Hotline. The Existential Crisis Hotline.
Dang, I'm not getting the ventriloquism thing. I've been practicing, and I keep forgetting it's when you don't move your mouth and you make sounds. But I always get it backwards. I have sort of ventriloquism dyslexia, so it's something I have to work on. But anyways, as I was trying to say, welcome back, everyone. Welcome if you're new. This is the Existential Crisis Hotline, and I'm Cameron Cope. And I see Sandra's in the chat. Hello, Sandra. How you doing? I'm going to pull up my Kick chat real quick so I can see that in real time. And I've got an interesting stream for tonight. Let's see. Here we go. All right, I got my chat popped out now. What's up, Sandro? I was just telling everybody how, or I was telling nobody actually, because I was muted. But I was trying to tell everybody how I am physically just wiped out. No, not actually, but my body is feeling very tired. Very actually relaxed. Today we took the, let's see, we have like 70 something chickens that we're raising for meat, and we have another 8 laying chickens that we bought just because my daughter wanted to buy chickens, although we don't need to buy them. But you know, she really wanted some, so we took them out of the little brooder area that I had made, and have this mobile coop with wheels. So I put them out on the pasture so they have fresh grass. We moved that around, so I had to get them all in there and move that out there. And then we also have some, actually no, I didn't have them in the brooder. I had them in the hey Gaitan, what's up? I had the 78 whatever chickens in the one of our smaller coops, and in the brooder we've got like 16 guineas and like 6 baby ducks. So I put those, so I took the meat chickens out of the red coop, put them out on pasture. Took the guineas and the ducks, put them in the red coop so they can kind of develop in there. And then we took all of the eggs that we were hatching, they're all hatched now, and we've got like 25-ish brand new baby chicks, and I put those into the brooder. So there's a lot going on in terms of birds over here at the TT Ranch. And then what else? Then I had to do the normal stuff like put the hay in the hay sacks for the horses, and put the hay for the cows. And that was all after this morning. So we have this like electric fencing, and we rotate our cattle around the pasture. So I had to make a new little section for them and put them over there, and we just kind of rotate them along so they have fresh grass. So, yeah, it was a lot, and it's not that, the work is not that hard, it's just so hot and humid outside. So I think that's really what does it. It just makes you, it just drains you, you know. But I'm feeling pretty good, pretty relaxed, and got some cool stuff for tonight. I was going to show you this first. Just thought it was kind of funny. Let's see if I have it up here. So I had left my computer unlocked to I think I was uploading something. I don't know. I just forgot to lock it. Anyways, um, Seneca, she comes over to me earlier and she says, "Hey, I just want to let you know I was looking up some stuff online because I needed to know some information." So I was like, "Okay." So then when I got back over here, this is what she was looking up. She had the Wikipedia page for uh, Atropa belladonna, deadly nightshade. She's got a deadly nightshade search, and they're talking about nightshade. What's this? Another nightshade plant. And so she was over here. She's 7 years old. She's over here doing research on nightshade. And it's just cool because lately, like the kids during the day, all three of them will go out together and they're like looking at different plants out on the property. And I swear they know so much. They have this book that I had bought years ago, like in Las Vegas. And I don't know if you've ever been to Las Vegas, but there's the Las Vegas Strip, which most people know, but the surrounding Las Vegas is the kind of like the total opposite of the Vegas Strip. It's so weird. And we went there for an event. This was like in 2015. We went there for a conference kind of thing, and on the Strip. But then Katie and I, we like went out and like we hiked in the desert. It was super cool. It was like a park, but it was kind of like desert like, and we hiked around there. And there was this one spot we found. It was like a literal oasis in the desert, like a literal one, like water with like plants growing and stuff. It was really cool. I don't know if it was artificial or what, but that was pretty neat. We hiked around a bunch, and they have like, it's like the Vegas outside of the Strip is like a hippie paradise. It's like juicing shops and vegan stuff and everything. It was kind of surprising. I wasn't expecting that. So anyways, so in one of these shops, I got a book about like edible plants, and we just had it on our shelf. It's like this thick. It's by Marcus Rothkranz. And anyways, so they have that book, and they've been like reading it and like talking about it. And then they're going out in the yard. Well, I say yard, like out in the property, and like identifying all the plants. And there was one time, this was like maybe like a week ago, I went out with Max and Caius, and they just wanted to go walk around. So we were going down this one part. It's like a little rocky area, like a slope. We went down there, and there was all these plants growing because I had it mowed there. And Max was like, "Oh, whoa, this is crazy. There's all this heel all is what it's called. I didn't even know about it." And he just noticed it, and he's like gathering it up and bringing it back. And apparently, it's this really great. Here, I'll look it up. Heal. I have to click on the page. Heal all. Yeah, this is the plant. Prunella vulgaris. Common self-heal, heal all, different names. And yeah, that's what it looks like. And it's just cool because they're reading these books, and it's like they remember what everything look. They're not taking the book with them in most cases. They just are reading it, absorbing it, and then they're noticing all these plants. And then like earlier today, they brought all these branches from a tree into the house, and I was focused on doing stuff. Katie was like, I think milking the cows or something. And so anyway, why does my picture look so small? I don't know what's going on there. Hold on a second. Option. Is it option? Whoa, there we go. I don't know if I want it that big. I'll do it like that. There we go. So anyways, what was I saying? So they brought like all these branches of some tree, and they were telling me about it, and they said it was some plant called Vitex, I think. Vitex. Yeah, Vitex tree. Yeah, so this plant. And Max goes, he was like, yeah, it's really good for women's issues. And I was like, women's issues? Like, what do you mean? And he goes, well, it helps women with progesterone. And he's like telling me all this about it. So, anyways, there's one of these trees growing in our yard, which I never really noticed. It's right by our garden, like next to a. It's like there's a sycamore over there. There's like an oak tree. There's an oak tree. Yeah, there's an oak. There's like a cedar tree, and there's one of these plants growing there. So they brought some of the branches in, and then later I went back into the house. Yeah, chaste tree. Oh, an aphrodisiac. I was wondering why they were calling it that. They were saying the chaste tree is called chaste. So, anyways, maybe that's just some mythological stuff. But, anyways, I came back in a little bit later, and I mean, keep in mind, like, this is just the kids doing their thing, right? There was like 3 cups next to the kettle, and I looked in the cups, and they had them filled with water, and they had like the parts of the plant in the tea. They were like making tea for themselves out of this stuff, right? And they were like looking it up, and they came and asked me like, "Is this what it is?" And they looked it up and everything. So we made sure like it's not. And we looked. They even said, "Let's look up. Does it have any lookalikes?" So we're looking up what are all their lookalikes. And okay, there's this other one, but the flowers hang down. Okay, that's not this because they're standing up. Like they're checking all this, and I'm obviously helping them look at it, but I'm more just there to make sure that they're looking at the information. I'm not doing the research for them, if that makes sense. And so they've just been going out in the property, like looking for stuff and identifying it. And I think that's why they were interested in the nightshade, I'm guessing, because I don't know why else would they be looking that up. And what was the other thing they found? Oh yeah, Max was showing me. We were out walking one day, and he was like, "Okay, do you see this one?" And I don't remember the name, but it was some kind of like relative of poison ivy. And I was like, "Is it okay to be touching it?" He's like, "Yes, this one's not actually poisonous, and you can tell because it has like these ridges on the leaves." He's like, "They're kind of sharp. You can feel them, right?" And so like they're like educating me on all the different plants on our property. It's really really cool. If you go out in the woods with them and there's a lot of mushrooms, they can pretty much identify what all of them are. It's like there'll just be some random one. I'm like, "What's that?" They know what it is. It's really really cool. So that's kind of just a testament to you know their vocabulary, their ability to read. Because I mean, would most people find a book about plants interesting? I mean, this is like not some kid's book. It's like a guide to edible plants with all the pictures and the species name and where does it grow and all the different features of it. And they just read stuff like this just because they can, but then they go and apply the information. It's so cool to observe. So, anyways, that was just my proud parent bragging section of today's stream. Um, oh, that reminds me. Today's June 1st. It's the beginning of Pride Month. So happy Pride Month, everybody. I was telling Katie, because somehow Pride Month, because somebody was texting me about it. And I had to look it up. I was confused. I just thought Pride Month was sort of like a Discovery Channel thing. Like how they have Shark Week. I thought it was just a month where it's like all about lions. But apparently it's not. Apparently it's about something else. But what did I want to talk about tonight? What I wanted to talk about, although my mind was a little bit distracting me on other topics, I suppose, I wanted to talk about something that's near and dear to everyone's heart. Something that you all deep down really want to know about. And that is quantum mechanics. Everybody, I know, everyone sits around thinking about quantum mechanics and wanting to learn about it and want to know what it's all about. Well, I understand. I can relate to that. And I've been reading this book by Werner Heisenberg, which I talked about previously, called Physics and Philosophy. And it's really good. It's really good. It's written in a way where it's technical, but not technical in the sense of mathematics and you have to have a strong math background. It's just technical in the sense of he's kind of speaking to other science-minded people, I guess, or philosophy-minded people. So he's not speaking to the layman. It's not a popular book. It's not a book of like popular science, but it's not a heavily technical book. I got another book by Heisenberg. I don't know if he wrote it or it's just a collection of some of his writings. It might be a book he wrote, called Foundations of Quantum Mechanics, and it's just math. It's a lot of math, and that's a very different book. But the book Physics and Philosophy, I think really anybody could enjoy, and it's cool because as I'm reading it, I'm sort of looking at how most people understand quantum mechanics. It's a word that I guess I can't say everybody's heard because I'm sure there are probably many people in this world who've never even heard the words before. But at a certain vocabulary level in society, most people know the word quantum mechanics. If you went to high school and you studied physics, you've probably heard about it. If you went to college and took physics, you've probably, I would say, definitely heard about it. And we've talked about different topics like that on the stream before. But I was kind of doing a little bit more like digging into it. And it's interesting because what I found is that, okay, I'm gonna kind of make some assumptions. But I think the average person who would be aware of quantum mechanics, okay, I think they would have the assumption that it's sort of the cutting edge of scientific theory. And the more I look at everything, and I've been looking into like modern physics, it's really not. And some people might not be surprised by that statement, but I think a lot of people might be just because of the assumptions that we have. And perhaps that's partly because if your science education ended in high school or college to the degree that you weren't like a physics major, although honestly I don't know what physics majors even study. I wonder if they go beyond quantum mechanics in a typical physics curriculum as a physics major. I'm going to look that up. Typical university physics major curriculum. Wow, I can't spell tonight. I'm just gonna not spell it properly. Okay. Thank you. Yeah, like I said, I'm a little tired today, but it's okay. I'm still here. Okay, let's look at UT Austin. That was one of the schools I was considering going to when I was applying to colleges. I got in there. I actually got a scholarship to UT for engineering, but I did not go there. Or I was offered a scholarship anyways. Okay, let's see. Option 1, physics, radiation physics, space sciences, biophysics. Okay, let's just look at physics. Okay, this gives a strong foundation for graduate study or work in physics. All right, so this is like you're a physics major. So you do some chemistry, 6 semester hours in biology, so other sciences. Physics 301, okay, and then they have some mathematics courses. I wonder what math they have to take. Okay, differential and integral calculus, that's not surprising. Sequences, series, and multivariable calculus. So that's basically what they would call analysis. Although, no, multivariable. Okay, that's just basically multivariable calculus. Okay, so that's like what you would call Cal 3, basically. Differential equations, okay. Advanced calculus for applications, Fourier series, partial differential equations, okay. Advanced calculus for applications too. So matrices, vector analysis, functions of several variables, gradient, divergence, curl, vector field, multiple integrals, Green's theorem, complex analysis. Okay, I mean it's a pretty strong math background. The following courses are recommended. Matrices and matrix calculation. Okay, so that's more linear algebra. Okay, so basically complex analysis and probability. Okay, not really that fundamentally that much different than what I would have studied as a math major. Physics 301, mechanics, laboratory, electricity and magnetism, laboratory, wave motion and optics. Can you bring your mic in or turn your volume up? Oh, is it like low? I'm pretty close to it. Yeah, I can raise it up. Let's see it. Does that sound any better? I'll keep talking and then you just tell me otherwise. I don't know why it's so low. Maybe I'm just speaking low. I'll shout these things. Okay, so optics, wave motion. Okay, so waves. And then what else? Another lab. Okay, so far pretty basic physics. Now let's see what they're doing over here. Classical dynamics. Okay, so this is still Newtonian stuff. Electrodynamics. Okay. Modern physics. X-ray diffraction, photoelectric effect, black body radiation. Modern physics, probability, special relativity, statistical physics, quantum physics. Okay, so they get a little bit of quantum physics there. Thermodynamics, more quantum physics, and then advanced laboratory, modern experimental techniques. Okay, let's see what else they get. One of the following: classical electrodynamics, quantum physics 3, particles and nuclei, thermodynamics, foundations of quantum physics, and then some more advanced. Did I click on this already? Or does it just look similar to the other ones? I literally just clicked on these. Oh, okay, I see what happened. I clicked up instead of on staying on this line. Quantum physics, cosmology. Okay, I don't care about that. Intro to relativity, cosmology, solid state physics. Okay, interesting. So that's your typical. So they're not even getting into anything really advanced. Radiation physics. It's all your basic stuff. I wonder what this is. Do we see this already? Classical dynamics, electrodynamics, quantum. Yeah, it's very similar stuff. Nuclear power. Okay, so it's for like more of like a nuclear type specialization. Okay. Space science. Okay, cool. Wow. So yeah, what I was looking for is how far are they going beyond quantum mechanics, quantum physics? And the answer is not really not at all. And so I'm reading this book by Heisenberg, Physics and Philosophy, and he makes this point in there that scientists and philosophers come up with terms for things that they're trying to understand. They come up with these words and terms and concepts, and they know that they're not actually the thing that they're trying to understand. It's just a name for it. It's not complete. And he makes this point that, ultimately they'll probably be superseded by other understanding. And so even if you go all the way through a physics degree from a reputable engineering school like University of Texas, Austin, you're not going to go beyond quantum mechanics. But quantum mechanics was conceived and mostly developed in like the early 1900s to probably 1930s, 1940s. And then they were developing the nuclear or the atomic bomb. So, why am I rambling about all that? Because I was watching an interview the other day, and it was really interesting because it's this guy. It started with an interview with this cognitive scientist, so he's not even a physicist. And he was talking about all of the limitations of quantum mechanics. and saying that at this point, like the cutting edge modern physicists, now they're specialists. So if you're just doing physics in a laboratory, you might not be trying to go beyond quantum mechanics, I suppose. But a lot of the cutting edge researchers in modern physics are already seeing that the quantum mechanical model is not a complete model. And this is something that probably already most people who have any kind of science background already know. And if you ever heard of, Einstein was looking for a unified theory, right? The whole idea of the unified theory in that context is they're trying to figure out how relativity theory and quantum mechanics can be unified, because there's sort of like, I don't want to say contradictions, but they, in the same sense that Newtonian mechanics describes the motion of things like in our normal like day-to-day life, relativity theory describes what happens when you're going like really close to the speed of light. And they had to come up with new ideas about what gravity is based on that. That's why they had to move from Newtonian to relativity, because they were like, oh, Newtonian mechanics only really applies when you're not going anywhere near the speed of light. Okay, and I'm going to get into a little bit more details about what I'm talking about here, because I know I'm speaking in generalities, but I'm just trying to give some context first. And then there was also quantum mechanics. And I don't know if many people really understand the distinction between relativity and quantum mechanics. It's probably not a clear distinction. They might know that there's a distinction. I don't know if the average person even sees that there's a distinction. They're just words they heard. They may not know anything about it. But there's a kind of fundamental disconnect between relativity theory and quantum mechanics. And I'll do my best to kind of give you my perspective of what I understand about it, and then maybe we'll look at some things so you can get like another more detailed, elaborate perspective. But the problem with, for example, quantum mechanics versus relativity theory is based on the idea that the space-time reality that we live in, as you move closer to the speed of light, time slows down and mass increases. And so the more energy you have, the more mass you have. Okay, that's if you look at E equals mc squared. Okay, now this can be relevant in a second. Now, when they're looking at the particles that make up our reality, right? So that's what scientists have been interested in for a long time. What are the fundamental particles that make up our reality? And then somebody came up with the idea of atoms. Now you can go all the way back to ancient Greece, right? I'll give you an example. You've got this guy, Democritus. And this was 460 to 370 BC. He formulated an atomic theory of the universe. If you've ever taken a physics course, you might have heard that. If you've ever taken a philosophy course, like especially if you've done like Western philosophy, you would have probably started with the pre-Socratics, so before Socrates, and you would have learned about Democritus and Anaximander and Anaximenes and all the other guys. And they all had sort of their own ideas about what is reality made of. But what's really cool when you read that physics and philosophy book by Heisenberg, he makes this distinction that the philosophers were sort of trying to describe reality in a qualitative sense. So some of them thought, maybe reality maybe it's fundamentally all based on water, because we know water can be solid, liquid, or gas, and it has all these different properties, and it seems to be in everything, like it's makes up a lot of our body, or different things like that. And somebody else says, well, actually, I think maybe the fundamental substance of reality is fire, because fire is both physical and it's energy and it produces light. Like they would have all these theories that they would come up with, but they're like qualitative. And Heisenberg explains how when we shift into like more modern physics, like post-Enlightenment physics, they started being able to do experimentation. And so the Greeks didn't really do experimentation. They just came up with theories and like just thought about it. But when you started introducing experimentation, you could say, okay, what is everything actually made of? Let's look. We've got microscopes. We've got different instruments that we can use to make observations. And so at a certain point, they started thinking about the fundamental substance of everything, and that's when the theory of the atom was created by like Niels Bohr. And then they realized that there seems to be like a positive aspect of it, a negative aspect. They started doing experiments like the gold foil experiment. I'll show you that. And these are all things that you would have learned about if you took any courses in physics. Or even actually if you took chemistry too. If you took chemistry in high school, they would have talked about this. So let's go back to J.J. Thomson. Where is he? It just mentioned him there. So we have, okay. So here's Thomson's model of the atom. So I want you to imagine they're taking the ideas of the Greeks from a certain perspective, and they're saying, okay, maybe everything is made up of some kind of like basic building blocks. And this guy, Thomson, he came up with the idea that the atoms had a structure like plum pudding. So they're kind of like positive and negative all kind of mixed in there. Let's see what it says. Thomson had discovered the electron through his work on cathode rays and proposed that they existed within atoms, and an electric current is electrons hopping from one atom to an adjacent one in a series. So they're kind of guessing and then testing to see if these things are correct. There logically had to be a commensurate amount of positive charge to balance the negative charge of the electrons and hold those electrons together. Because if they were all negative, they would just fly out right away. So there had to be some positive. Having no idea what the source of this positive charge was, he proposed that the positive charge was everywhere in the atom. So that's like the pudding, and then you've got like the raisins, which would be like the electrons all scattered about, right? So that was the idea. So then this other guy, well, there was different objections to it, but then this guy Rutherford did an experiment called the Rutherford scattering experiments. Okay, let's see if they actually talk about it. Scattering theory. Okay, so did they already talk about it? Oh, I skipped it. Here we go. So Rutherford, let's see. He sought to determine the charge and mass of alpha particles independently. Where did they talk about alpha particles? I skipped ahead way too much. I'm trying to figure out where they talk about why did they even think of them in the first place. Okay. Okay, so they knew about alpha particles, a positively charged particle of matter that's spontaneously emitted from certain radioactive elements. So they knew about these things. Alpha particles are so tiny to be invisible, but they can be detected with the use of phosphorescent screens, photographic plates, or electrodes. So Rutherford discovered these. In 1906, by studying how alpha particle beams are deflected by magnetic and electric fields, he deduced that they were essentially helium atoms stripped of 2 electrons. Thomson and Rutherford knew nothing about the internal structure of alpha particles. They didn't know how many electrons a helium atom had. Okay, so Thomson's model was consistent with experimental evidence at the time. Trying to see where they talk about how they discovered the proton. The experiments they designed involved bombarding metal foil with a beam of alpha particles to observe how the foil scattered them in relation to its thickness and material. Each impact of an alpha particle on the screen produced a tiny flash of light. Geiger worked in a darkened lab for hours on end, counting these tiny scintillations using a microscope. Okay. In 1909, Geiger and Marsden discovered that the metal foils could scatter some alpha particles in all directions, sometimes more than 90 degrees. This should have been impossible according to Thomson's model. Because, according to Thomson's model, the positive was all throughout the whole thing. But what they noticed was only in certain spots would it scatter the alpha particles, because an alpha particle is positively charged. So if you're shooting a positively charged thing at a generally positively charged thing, it should always basically bounce off unless it hits an electron. But they noticed in some cases, like in this picture over here, they would go straight through, and sometimes they would go straight through and sort of be deflected, which would imply they were influenced by like an electron. But sometimes they would just go straight through, and only sometimes it would just bounce off completely. That's where they started to get the idea. When they figured out all the ways in which it bounced off and looked at the pattern, they were like, oh, this points to the fact that actually the whole thing isn't positive. There is a positive thing in there, but it's kind of located in the center of the atom. And according to the scattering effects, they could deduce that the electrons were kind of like somehow outside of that central positive part, but not necessarily everywhere. So this is kind of how the understanding of how an atom is structured got to be developed, by doing these experiments. Okay. But look, this was all done in like early 1900s. Right? Just seeing if there's anything else worth looking at here. So let's look at the Rutherford-Bohr model. In atomic physics, the Bohr model, or Rutherford-Bohr model, it's obsolete, okay, but it was a model of the atom that they came up with. Now we'll look at why it's obsolete. So it was developed by Niels Bohr, building on Rutherford's discovery of the atomic nucleus. It supplanted the plum pudding model. So they knew there was something positive, but they still didn't know how the electrons worked in relation to that. So Bohr came up with an idea of how the electrons existed in relation to the central positively charged thing. And basically his general model was that it says it consists of a small dense atomic nucleus, that would be where the positive would have been, surrounded by orbiting electrons, analogous to how our solar system works, but with attraction provided by electrostatic force rather than gravity. So if you think about our solar system, you have the sun and you have the planets going around it, and they're held in place by the gravitational attraction between the planets and the sun. In this case, though, they were saying, well, it's not gravity that's doing it, because the things would be so small that the gravitational force wouldn't be enough. So there must be some kind of electric force, which makes sense because they're positive and negative. So they're kind of orbiting around the nucleus of the central positive nucleus. The electrons are orbiting around it. And it looks like, at this point they also theorized that the electrons weren't all just in one central thing, one central orbit. There was like levels to it, like different orbits, kind of like the planets. Like they don't all go around in the same ring. There's like Venus, and then out here is, is it Mercury, and then Venus, and then further out is the Earth, and then Mars, and so forth, right? So that's how that was the model they came up with. But notice, like, they don't see the thing directly. They're doing these experiments where they're seeing how things bounce off of stuff, and then they're kind of trying to work out, okay, what would this thing have to look like if this is what we're seeing, like, based, if we're seeing the particles are scattering this way, then maybe it looks like this. Okay. So over time, they're developing a picture of how they think this thing exists. But that tells you right there, they can't just see the thing directly. They can't just see, oh, look, there's the atom, and there's the nucleus, and there's the electrons, and so forth. But again, this is like 1900s. When was this model? Developed from 1911 to 1918. Now ask yourself, how many people, if you pressed them and they had to give you an answer, and you said, how do you think atoms work? Now you might get an answer like, oh, I don't know, that was a long time ago, I don't remember any of that stuff. Or if you pressed them, I think most people, if they give you any answer, would say, oh yeah, I remember, you've got like the nucleus, or maybe you don't remember the name. You have the part in the center, and then you have like, maybe they'd say electrons, and they're like orbiting around the nucleus, right? I would say that's probably most people's understanding of it, because that's a picture that you can visualize. But look what it says. It's obsolete. Now, I don't know how I could verify my assumption here that this is probably the picture in most people's head, but I was a tutor for a very long time. So I know, like the back of my hand, what's taught up through high school. And I went to college, so I know what they teach in college. Of course, not every single subject, but I did a mathematics major, so I know what they're teaching there. I took several semesters of physics at a top engineering school, so I kind of know what's in the curriculum and so forth. And we just looked at UT Austin, like what's in their physics curriculum. So they're talking about quantum physics and so forth, right? So let's look at that for a moment, okay? Let's look at what replaced the Bohr model of the atom. The quantum mechanical model. Okay, cool. I wasn't sure if there was something in between or not. Okay, so let's look and just see what it says here, and then maybe we can break this down a little bit. The quantum mechanical model, also known as the wave mechanical model or electron cloud model. Now, when I say electron cloud, some people are like, oh, yeah, that takes me back to chemistry. I remember the electron clouds. Yeah, they're like clouds somehow. It's a cloud. I don't know. What the hell does that even mean? But that replaced the Bohr model in the 1920s. Developed by physicists like Erwin Schrödinger and Werner Heisenberg. It treats electrons as three-dimensional waves rather than as tiny planets in fixed orbits. Why the shift occurred? Okay, and this is the part that's so fascinating to me, is this right here, this Heisenberg uncertainty principle. So the Heisenberg uncertainty principle says that it's mathematically impossible to simultaneously know both the exact position and momentum, which would mean like, so the position is where it's at, and the momentum is sort of like where it's going and how fast. So what direction is it moving in, and how fast is it moving in that direction? That's what momentum means, right? Sandra said, you're still picturing the Rutherford model? I was still thinking about plum pudding. Okay, so why is that? Like, okay, again, I don't know how much each person individually remembers what you were told in high school, but I know for a fact you were told this. Like, unless somehow you got through high school without taking chemistry, and I don't know. Like, I went to a private school, so maybe I have a little biased perspective, but I also tutored people in public schools and so forth. So I'm just talking about America. I don't know about other countries. We could probably look it up, but the point is, you were told about this. There was a section when you took chemistry about electron configurations and these little diagrams where you draw boxes and you put little up and down arrows and you give the electron configuration for a particular atom. So if you were learning that, you were actually learning some kind of version of the quantum mechanical model. You weren't learning quantum mechanics, but you were learning some of the general conclusions that came out of it. Okay, but anyway, so Heisenberg, you probably learned about the Pauli exclusion principle. You learned about Heisenberg's uncertainty principle, and you would have learned about, I say learned, you would have been told about, there's one more, what is it? Pauli exclusion, Heisenberg uncertainty, and the Aufbau principle. That would be the other one. Those three I know are like big, those are the ones that are really hammered in the high school chemistry curriculum. And actually, I don't think you really learn much about that in physics. In physics, now, I didn't take honors physics in high school, so I can't really speak to what they studied in honors physics at my particular high school, but our standard physics course was still pretty, actually, maybe it was honors. I actually don't remember. whether it was or wasn't. It might have been honors. But either way, we didn't really go into much of this. Although there was a certain point I remember where we talked about quantum mechanics. And when I was in university, there was a part of one of the semesters where we talked about quantum mechanics. I'm trying to remember if that was actually an entire course or not. It couldn't have been, because we would have gone into way more detail than just what I remember. But I remember us doing some version of the double slit experiment. But I was not really that interested in any of it at the time. So I can definitely relate to being in a class and being told a bunch of information and not remembering any of it. I just remember, oh yeah, we talked about it, but I don't really remember what it was all about, just from what I experienced in school. In some classes I remember, some I don't. So I think that's kind of applies to everybody, really, except for like the really studious students. Okay, but let's go back to this. So the Heisenberg uncertainty principle. So this was something he came up with, and then it sort of steered the direction into quantum mechanics. And he explains this a bit in that book I was talking about, that Physics and Philosophy. It's mathematically impossible to simultaneously know both the exact position and momentum of an electron. Therefore, precise orbits cannot exist. Now that's weird, right? Like, if I didn't already know anything, I would say, okay, I'll take your word for it that it's impossible to know the position and the momentum. But why would that mean precise orbits can't exist? Couldn't it just mean you don't know what they are? Like, hypothetically, if for some reason I could not measure both the speed and position of a baseball that's being thrown, you're telling me it didn't go in a specific path? Because, like, okay, if I throw a baseball, it travels through a very specific path from my hand to the person catching it. Now, even though I can't know, hypothetically, according to this, now this doesn't necessarily apply to baseball, but I'm saying let's assume it did. Even if I couldn't know for sure at any given moment of time the exact position and momentum of the baseball, why would that imply that it doesn't travel through a specific path? Do you see like why that doesn't intuitively make any sense, right? But again, we're not talking about baseballs. We're talking about the fundamental units of matter, or at least what scientists believe are the fundamental units of matter. Atoms, okay? Atoms and particles like electrons, like they're subparticles, like protons, electrons, things like that. So I don't think it intuitively follows that just because you can't know both the position and the momentum, that therefore a precise orbit doesn't exist. Okay? And he makes this point in the book because he says, well, why, he said at one point they came to doubt that perhaps they did follow a precise orbit. So they assumed they did. That was the Bohr model. And then at a certain point, some scientists like Heisenberg or others, and he didn't explain why, but I'm sure it's there somewhere in history, like explained. For some reason, they started to doubt that maybe the electrons didn't travel in specific orbits. And maybe there was some experiment they did that kind of showed otherwise. So they were like, And he said, so you might say, well, you could just get a really good microscope and peek in at the atom and look at the electrons, and you could be able to see them traveling in their orbit, right? Why not? And even if you don't have a microscope that good, you could imagine at some point maybe somebody could build one, and then we would know, right? That wouldn't imply that they literally don't. But he makes this point, first of all, that you can't build a microscope that does that. It's not possible because, and this is why I was talking about the E equals mc squared earlier, the way you observe an electron, think about those experiments we were talking about. How were they observing what was in the atom? They were shooting particles at it and seeing what happens when the particles bounce off. So they had like a photographic plate, meaning whenever the particle would hit the atom, okay, that was like in a piece of metal, and bounce off, if the whole wall is like surrounded with like, photographic paper everywhere, then whenever like the electron or whatever it is they're shooting would hit that paper, it would leave a little mark. Like if you've ever done any shooting at a gun range, they have these targets trying to remember what they're called. There's probably different names for it. But like when you shoot it, it's like black, and when you shoot it, when your bullet hits, it like it makes like a green mark. I don't know how it works, but there's probably like some like green paper underneath and like a black coating, right? Kind of like if you ever, like when you were a kid, you draw like rainbow colors on a piece of paper and then you cover it up with like black and then you scratch through it, right? You'll be able to see what's underneath kind of. So it's kind of like that. So imagine on the photographic paper, it's like it leaves a mark wherever it hits. And then you can go back later and look at the picture. Okay, we knew we hit this one at this direction. It bounced off here. We keep doing it and we have like a record of all these little marks, and we can see like all the different ways in which the particles scattered off of this object we were hitting it with. So in other words, they're not looking at the thing. This is what I was trying to say earlier. They're not looking at the thing and just seeing what it is, right? Like with a baseball, you could just watch it. You can see, I see it follows a specific path. It's not like going like boop, 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 popping in and out of existence until suddenly it just appears in the other person's hand. It follows a specific path. But you actually can't look at an electron in a way that allows you to know not only where it is, but where it's going at the same time. So you can't really keep track of it in real time. All you can do is see where it's at right now and then see where it's at later. Or you can see how fast it's moving now and you can see how fast it's moving later. Or some combination of where it's at and how fast it's moving, or how fast it's moving and where it's at. And so what Heisenberg explains in that book is that it's not that you just don't know what's going on in between. There is nothing happening in between. And he even said the word happening is only relevant to an observation. Okay, and I don't know if that like clicks. I feel like that's a thing where either like it makes sense when I say it or it doesn't, but I'll try to explain it. Like when I throw a baseball, I know it leaves my hand and I know it goes through the air in like an arc and then it lands in the other person's hand. So in between me throwing it and them catching it, these two different events, we know what's happening in between is it's moving through the air. And at any moment in time, I can stop and look at it. You know, like I could take a snapshot of it at any point and I know it went through this particular arc. But what they discovered with electrons, which are subatomic particles, you can't do that. You can only observe it at this point and then at another point. And what's happening in between is nothing is happening in between. Which sounds totally counterintuitive, right? But this is where the weirdness of quantum mechanics starts to come in, which is why, and I'm just giving you one example. We'll look further at this point, so don't worry. But I think this is why when you talk to people who know something about quantum mechanics at some kind of, more mathematical level, they'll say things like, anybody who claims to understand quantum mechanics doesn't. Like, it's like you can't really understand it, meaning it's so counterintuitive. It doesn't make sense. And yet it's what they've kind of developed an understanding of, meaning just because it doesn't make sense doesn't mean that's not what's happening. That's what we're observing. Okay, so why? Why is this the case with this uncertainty principle? Because an electron, remember going back to that point I was saying about how they're throwing particles at stuff and seeing what happens. So the only way they can look at an electron is by, looking at it, okay? But when you look at it, how do you look at something? Like if you're in a pitch black room, can you look at anything? I mean, you could look in the direction of something, but you can't see it. So you have to turn on the light. And when you turn on the light, then you can see it, okay? So I'd have to shine a light on it so that the light can reflect back and then I can see it. But electrons are so small that to very precisely see where they're at, where it's not just like a fuzzy image, right? Like if you've ever, like you have a phone, right? And you try to like put the camera like really close to something, how it looks all like fuzzy and blurry, right? So if you try to look really closely, and the way you look at something is you have to shine the light at a certain wavelength. Because if the wavelength is too big, it won't get the detail of the particular thing you're looking at. So if it's very small, it won't pick it up. It won't give you that information back. It doesn't bounce off of it. It just goes past it. So to make that wavelength small enough so that it can hit the electron and come back to you, the amount of there's a relationship in physics, which is the lower the wavelength of light, the more energy it has. Okay, so wavelength and frequency are inversely related, meaning the higher the frequency, the lower the wavelength. The higher the wavelength, the lower the frequency. And frequency and energy are directly related. Okay, so the higher the frequency, the more energy. So in this case, in order to look at the electron very clearly, you have to have a very tiny wavelength. But that would imply so much energy. Okay, in other words, a very high frequency of energy, high frequency wavelength, or a high frequency beam of light, that it would immediately like shoot the electron off somewhere. So you have this uncertainty about, well, if I know exactly where it is, I had to use so much energy, it's totally unpredictable where it's going. So this is where the Heisenberg uncertainty principle comes in, and they literally can't look at it. Let me see if I can find another explanation of it. Oops. Come on. Electrons. Let's see if they give an example here. Imagine trying to track a microscopic, fast-moving electron. In the quantum realm, observing a particle requires bouncing a measuring tool, like a photon of light, off of it. Because electrons are incredibly light, the mere act of hitting them with a photon transfers momentum. This collision changes the electron's speed and direction. So I'm trying to observe what the electron's speed and position is right now before I look at it. But as soon as I look at it, it's immediately changed. If you use high energy light to pinpoint the electron's exact location, you hit it harder, making its new speed and direction completely unpredictable. Conversely, if you measure its speed gently, you sacrifice details about its exact location. And see, what's interesting is it says the principle isn't a limitation of our cameras or lab equipment. It's a fundamental property of the universe. It's governed by this mathematical relationship. This principle completely changed how we view atoms. Previously, scientists thought electrons orbited the nucleus in neat defined rings, much like planets orbiting the sun. Because of the uncertainty principle, we know it is impossible to predict an exact path for an electron. Instead, we rely on probabilities. Okay. But again, intuitively, you would think, well, yeah, okay, we rely on probabilities because we don't know, but clearly it is somewhere, right? We just don't know what it is. So let's see, is that what it is? But is it the case that the particle has a definite momentum and position before being observed, but we just can't measure it? Let's see what it says. Look at that. No, it doesn't. What? Okay. So I'm just trying to represent, like, that seems weird, right? Now, if you were somebody who had studied quantum mechanics, you'd be like, dude, we already know this. Like, I'm not trying to pretend like this is new knowledge. I'm just trying to get across for the average person who hasn't studied quantum mechanics, and it's just kind of like a fuzzy idea, and yeah, things are weird, you know, and I don't know like what really much about it. I'm trying to just speak to that person right now, like, which was me before I started learning about these things, right? Like, okay, I get it. You can't measure the speed and the momentum, fine, but obviously it has a speed and momentum. You just can't measure it, right? And they're like, no, it doesn't have one. You're like, wait, what? But if it doesn't have one, how can you measure it? Well, okay, so I'm just trying to play the sort of devil's advocate is not the right word, but like the person who's like, what? This doesn't make sense, okay? No, the electron does not have a definite position and momentum before it is measured. What that implies is that it's not like a baseball traveling from here to there through a specific defined path. We just can't know the path because we can't see it, but it's definitely got a defined path, right? They're like, no, it doesn't have a defined path. I'm like, what? Why wouldn't it have a defined path? All things, like, you can't just be here and suddenly appear over there. And here's the big thing. It's like, well, hold on. Why do you assume that's how things work? Like, well, I observed that. Like, watch, let me throw a baseball. See? Now, the explanation would be, right, but that's a very large object compared to the size of a subatomic particle. So we're talking down at this very tiny scale. Things do not behave like they do in the bigger picture, like that we normally everyday experience. That's weird, right? What's going on there? How is that possible? Okay, so in standard quantum mechanics, it genuinely exists in a state of fuzzy probabilities until an observation forces it to choose a definite value. The idea that a particle has hidden properties we simply cannot measure is an intuitive trap. In other words, what I was saying earlier of like, well, okay, I get it. So this uncertainty principle, we can't measure it because you just can't get the light small enough without totally screwing up the, hitting it so hard with so much energy that it just flies off and you can't figure out where it went or what it was doing. Like, okay, I get it. It's some limitation of our ability to observe it. Fine. But clearly it's there and it has a momentum and a position just like a baseball. Like if I was blind and I'm like, well, if I could see the baseball, I know it would be in a certain place, but I'm blind and I can never see anything, so I'll never be able to observe it. But that doesn't mean it's not in a specific place, okay? Well, no. With electrons, with some atomic particles, they literally don't exist in a definite place before they're observed. That should be, I think, sort of a, what the fuck are you talking about? Like, what? How is that possible? That should be the kind of general feeling you have about it, right? That would be a normal response because everything about how you think about things is totally the opposite of that. Because think about it. So everything is made up of these tiny things that do not have a particular position and momentum. Okay? So everything is composed of that. But at some level, everything has a definite position and momentum. What the hell's going on? How is something with no position that doesn't even exist in a definite place until it's observed produce and combine together to make something that does have a definite position always? That should be like, what the hell? It turns out that thinking of an electron... Oh, look. It's like it read my mind. But that's how I used the example. I just didn't know I was going to use it. But it turns out that thinking of an electron as a tiny baseball is fundamentally incorrect. So it's proving my point. It's not correct to think about it like a baseball. It does not behave in the way you would think a baseball would behave. The electron as a wave. An electron is not a solid sphere. It has a wave-particle duality, which we haven't even talked about yet on the stream, or at least not in this conversation. When it is not being observed, the electron acts as a wave spread out over a region of space. Wavelength equals momentum. A wave's physical wavelength dictates its momentum. Yeah, see, like I'm just reading what Gaitan said. It sounds more like a justification for their lack of ability to see what's happening. I get that. But we'll look at that. We'll go further. A perfectly localized particle has no distinct wavelength. A perfectly steady wave with a measurable wavelength is spread out infinitely across space. Because an electron behaves like a wave, it is physically impossible for it to possess a sharp, localized position, and a sharp, distinct wavelength simultaneously. The uncertainty is built into the wave math itself. Let's see, what is this? Oh, what did I argue a point? Oh, okay, right, because I wrote this just to argue back, yeah. For decades, brilliant physicists like Albert Einstein actually argued your exact point. Wow, thanks AI. It knows how smart I am. Yeah, it makes sense. Einstein and I think a lot alike, so it makes sense. Einstein even agrees with me. Einstein famously claimed that quantum mechanics must be incomplete, proposing that hidden variables dictated a particle's exact traits before measurement. Okay, so even Einstein was unconvinced. This debate was settled by physicist John Stuart Bell through Bell's theorem, which was later confirmed by Nobel Prize winning experiments. So when you win the Nobel Prize, I mean, you're right. You know you're right, right? The result. Experiments prove that particles do not carry hidden, predetermined properties waiting to be uncovered. The reality. The act of measurement doesn't just reveal a pre-existing state. It actively forces the electron to collapse from a cloud of possibilities into a single reality. Yeah, let's see what it is. Let's see what it says here. Wow, who knew AI could be so useful, guys? Explain how Bell's theorem proved Einstein. Oh, I just missed it. Okay. Wrong. I was like, how is that misspelled? Okay. By showing that the universe cannot be both local and real at the same time. Einstein believed in local realism. This is the common sense idea that objects have definite properties before we look at them. Realism. And that cause and effect cannot travel faster than light. Bell proved mathematically that if Einstein was right, certain quantum experiments would yield a specific limited set of results. When scientists actually ran the experiments, the results broke Bell's limit every single time, proving Einstein's view of reality was incorrect. Here's how the proof works, using a famous analogy created by David Mermin. Okay. This should be interesting. The quantum sock machine. Oh, is that where all my socks go? Okay. That's why I can never find the other socks. They literally don't exist until I find them. Imagine a machine that creates pairs of socks and shoots them in opposite directions to two observers, Alice and Bob, who are far apart. Alice and Bob each have a testing device. This device can be set to measure one of three distinct traits of the incoming sock: size, color, texture. To make it simple, every trait has only two possible outcomes: size, large or small; red or blue, smooth or rough. Einstein's argument, local realism. Einstein argued that the machine prints these traits into the socks the moment that they're created. For example, the machine might create a pair of socks that are programmed to be large, red, smooth. Because the socks are a pair, they are perfectly correlated. If Alice measures size and gets large, Bob will automatically get large if he measures size. So in other words, if it shoots these socks out and Alice gets a large sock, clearly, if assuming the machine functions properly, Bob would get a large sock. Crucially, because Alice and Bob are far apart, Alice's choice of what to measure cannot instantly change the physical reality of Bob's sock. That makes sense, right? That would require spooky action at a distance traveling faster than light. So like if they're like light years apart, okay, they're super far apart. They both get the socks at the same time. Bob doesn't look at his sock. Alice looks at her sock and it's red. He looks at his sock. It's red. Okay. Seems like that would be pretty obvious because they're both red to begin with, right? Okay, all right. So, okay, let's see what's going. John Stuart Bell looked at this setup and asked a simple mathematical question. If Alice and Bob pick their settings completely at random, How often should their answers match? Let's assume Einstein is right, and every sock has fixed traits before leaving the machine. Take a sock programmed as large, red, and rough. Alice and Bob randomly flip their switches to check any of these three traits. What do they mean, flip their switches? Where did that come in? Did I miss something? Oh, it's the testing device. Okay. The device flipped the switch to test it. Okay. Alice and Bob randomly flip their switches to check any of the three traits. Look at the possible combinations of choices they can make. Alice checks size L, Bob checks size L, match. If she checks L and Bob checks R, no match. Okay, so obviously there's a lot of combinations there, right? Out of 9 total random combinations, they match in exactly 3 of them. That is a 33% match rate. Bell proved that no matter how you program the hidden traits across thousands of socks, if the traits are fixed in advance, random testing will result in a match rate of at least 33%. I'm not understanding the randomness. Let me go back to the setup. But it says the socks are a pair, they're perfectly correlated. I don't understand this random part. I have to look more into this, but okay, I'm gonna keep going. But I don't know if anyone else is confused. Like, where's this randomness coming from? If it's actually set to begin with, why would they ever check it and get a different answer? So, problem is it's an analogy, and maybe that's why it's confusing. It's also an AI, so it may just be like making shit up here. Okay, but there's something about it that doesn't make sense to me. Like, I don't understand why they would check it and not get the same thing. Okay, but we'll keep going. Maybe there's more we can look at. In the 70s and 80s, physicists like Alain Aspect built this exact machine using entangled photons instead of socks. They randomized the settings at the very last microsecond, so no signal could travel between the detectors in time. Okay. If Einstein was right, the match rate had to be 33%. The actual experiment, the match rate was under 25%. The experiment violated Bell's inequality. The only way to get a match rate that low is if the traits do not exist before they are measured. The particles do not leave the machine with fixed instructions. Instead, Alice's measurement actively forces her particle to choose a state. Instantly across space, Bob's particle alters its probabilities to match, even though no signal could have traveled between them. By proving that local realism cannot explain the universe, Bell's theorem definitively showed that Einstein's intuitive view of reality was fundamentally wrong. Would you like to try a quick interactive quiz to test your understanding? No, because I don't understand it. I think we need to understand Bell's theorem directly, because I feel like the analogy is kind of throwing me off because it didn't really make sense how it's randomized. Let's see if there's anything here. The analogy didn't make sense because I don't understand why they would, if they're physically, but again, it's an analogy. So that's where it kind of breaks down, because if it's making the socks in exact pairs, why wouldn't they ever measure something else? Why wouldn't it always be 100% is my point. So I just don't think the analogy is very helpful. Let's see if I can find something on YouTube. Minute physics, EPR paradox, Bell's inequality explained. Let's see what he says.
Two of the biggest intellectual giants of modern physics changed our view of reality and proposed their theories around the same time in the early 20th century. Yet their views about reality were completely different. Niels Bohr, one of the founders of modern quantum mechanics and the father of the Copenhagen interpretation, argued that reality, or the state of a particle at the fundamental level, was not only unknown, but was unknowable until it was measured. Albert Einstein passionately disagreed with this idea and believed that reality was knowable and that probabilities could not completely define reality, that there had to be an objective reality out there independent of measurement. He famously said in his dramatic statement, "Do you really believe the moon only exists when you look at it?" Bohr and Einstein argued passionately about their views on the essence of reality, and for 30 years both views were considered equally valid, and scientists chose.
So, okay, before we go further, this is really interesting, but think about this. Intuitively, common sense, you're like, well, of course, the moon is there, whether I'm looking at it or not. And like we were talking about, I remember like the whole tree falling in the forest thing, right? Because I was saying obviously it falls, whether it makes a sound or not. The experience of the sound doesn't occur because there's no one experiencing the sound, but the sound is occurring. But what they're suggesting is there ain't even a tree falling at all, which it's like, okay, so what the fuck does that imply? Would that imply that, well, maybe I don't want to go there yet, but the point I was going to make when I stopped the video was, you could say, okay, of course the thing exists when we're not looking at it. But then you should be able to do experiments and it should confirm that reality to you when you do the experiments. And so I'm not per se saying that they are correct. I'm just saying what it appears is that when they started doing the experiments at a very small level, like with electrons, be like, okay, well, of course it exists when we're not looking at it. Let's prove it. Like, let's observe it and so forth. They started running into these contradictions to that common sense intuitive viewpoint. Like results that they're like, these results don't make sense. These results would seem to more indicate it's not there. Okay, so again, I'm not saying that proves anything. I'm just trying to give you like kind of an insight into seeing what they were doing. They weren't just saying like, no, I think nothing does exist until you look at it, and they're just like assuming it. They were doing experiments, and because of the results they were getting, they were like, huh, this is weird. That's not what we expected. Why is this occurring? And they would do more experiments, and the experiments would start to kind of confirm the opposite view. And Einstein was not an experimental physicist, so I can understand, and again, that's not to say that the experimental physicists were right, but my point is, they're doing these experiments, and Einstein's kind of like, I mean, come on, guys, like, that can't be real, right? Like, come on, there's got to be something else going on here, because obviously things exist when we're not looking at them. But they're like, look, Einstein, I get it. I feel that way too. However, when we do these experiments, the information we're getting back from it seems to contradict that. So what the hell is going on here? Okay, so that's just kind of the backdrop of all this.
Those sides. Then in 1964, Irish physicist John Bell devised a way to prove whether Einstein's view of a classical deterministic view of reality was correct. And he put this in a simple, elegant equation called the Bell inequality. Although the equation is simple, understanding what it means is not so easy. So how did this simple equation disprove the ideas of the most famous and powerful scientist of the 20th century, and forced us to confront the unsettling truth that we may live in a fundamentally non-deterministic universe. The answer is coming up right now.
Okay, now let's think about that for a second, though. What did he just say? Confronting that we don't live in a fundamentally deterministic universe. So if it's the case that everything already exists exactly the way it does, wouldn't that kind of imply that, okay, everything exists in a certain definite way, and then things are in motion, there's forces, there's reactions, there's interactions. Where is there any choice whatsoever in anything? Like, if you assume, okay, no, of course it's there when I'm not looking at it. Which, again, I'm not saying it's not. I'm not trying to prove it one way or the other. I'm just trying to look at all the different sides of the argument, right? If we go with the point that, of course it's there when I'm not looking at it, then that means every chemical in your body, every atom, everything is there when you're not looking at it. Everything's already determined. And then they're interacting with each other. Okay? They're interacting with each other. So the outcome is already determined. And that outcome of that interaction is determined. And the outcome of that interaction is determined. So if you find comfort in the idea that, of course, everything is determined, doesn't it kind of logically lead to a point that everything's determined? There is no actual choice. There is no free will because it's all determined. Like, you're just the result of interactions. There's no choice whatsoever. So from one perspective, you could say, if it's not fundamentally already determined and somehow we're determining it in some way from a sort of undetermined level into a determined way, that sort of opens the idea that, oh, maybe I can determine things to be a certain way or not. So it opens up the idea of like choice, free will to some degree. Okay, so I'm just playing with the ideas with you guys, right? All right, so let's keep going.
Before I talk about the EPR paradox and Bell's inequality, I want to point out that part of my inspiration for this video was from a documentary that I watched on Magellan TV. Magellan TV has an exclusive offer right now, link in the description. The central weirdness of quantum mechanics can be demonstrated with the toss of the dice. If the dice was a quantum system like a photon, electron, or atom, it would be in superposition. That is, its position and other properties, in a sense, would be up in the air, like a dice thrown before it hits the table. It's a 1, 2, 3, 4, 5, and 6 all at the same time. According to the most accepted interpretation of quantum mechanics, the Copenhagen interpretation, pioneered by Niels Bohr and Werner Heisenberg, it's not only that the dice's value is not known, but that it is all values at once. Its value can only be known once it is measured. The double slit experiment demonstrates this. A single photon passing through the slit should not be thought of as a particle going through and interacting with itself. Rather, it's like a three-dimensional wave or cloud of probability when it is emitted. This wave can go through both slits at once and interfere with itself like a wave does before it is measured by the photosensitive screen in the back when it resolves to a specific location on the screen. Einstein, who was the most famous scientist at the time, was bothered by this interpretation of quantum mechanics. The idea that part of nature remains not only unknown, but is unknowable unless measured. That's why he famously said, God does not play dice. So Einstein, along with two other scientists, Boris Podolsky and Nathan Rosen, EPR for short, came up with what they thought disproved the Copenhagen interpretation. The crux of their argument rested on the idea of a phenomenon predicted in quantum mechanics called entanglement. Let's say we have a quantum system that has zero angular momentum, also known as spin zero, and it emits two photons simultaneously. Since photons have spin and since angular momentum must be conserved, if one photon has a spin up, the other photon must have a spin down. So the spin up and down cancel each other out. This is entanglement. The two photons are not independent. If the spin of one of them is known, the spin of the other becomes known instantaneously. Now let's separate these photons far apart, let's say 300,000 kilometers, which is about 1 light second away. Now according to quantum mechanics, each of these photons is governed by a wave function. And each photon is...
So in other words, according to quantum mechanics, neither one of them already has a determined spin. Okay, that's I think what he's getting at. They don't have a spin. Neither one of them has a spin, but it would be the case that whatever spin one eventually does have, the other one has to have the opposite spin to cancel out and conserve momentum.
in a state of both spin up and down at the same time. It is not up or down, it is both up and down. However, the wave function of these photons is not independent. They're really the same wave function governing both photons. Now, if we measure the spin of one of them, we have a 50% chance of detecting a spin up. Let's say we do detect spin up. Now let's measure the spin of the other photon in less than 1 second.
Okay, see, this is making, and I know this isn't the Bell experiment, this is EPR, but still, this makes a lot more sense than the SOC one, because they're saying they're randomly ejecting these two photons. So there's a chance that they have up or down. It's not determining it from the very beginning. The SOC thing didn't make sense because how do you make the machine that doesn't determine what the properties are? So that's why I was like, I don't understand why there would be any randomness. But this makes sense. It's randomly ejecting these two particles, whatever they were called. And what's the chance that one of them would have a spin up? It would be 50%. It's either up or down. So 50% chance the one I'm measuring will have an up spin, right? Okay.
Second, it should also have a 50% chance of having spin up or spin down, but it doesn't. It has a 100% chance of having a spin down. This means that the information of 100 have now 50% chance of detecting a spin up. Let's say we do detect spin up. Now let's measure the spin of the other photon in less than 1 second.
Okay. Wait, did he say that they measure it and it has a spin up? Because he still has a 50% chance on there. I'm going to start it over again.
One of them, we have a 50% chance of detecting a spin up.
Okay.
Let's say we do detect spin up.
Okay, so it has a 50% chance, and then we actually detect it, and we detect that it has a spin up. So then what are the odds the other one has a spin down? Obviously, if we already know that one is spin up, the odds now of the other one having a spin down is 100%.
Now let's measure the spin of the other photon in less than 1 second. It should also have a 50% chance of having spin up or spin down, but it doesn't. It has a 100% chance of having a spin down. This means that the information of the collapse of the wave function of one of the photons had to travel faster than light to affect the other photon.
So in other words, if they didn't already have the properties, but they were entangled, meaning they came from the same source, so if one is up, the other one has to be down. Kind of like if you have a banana and you cut it in half, one has to be the top of the banana and the other has to be the bottom of the banana. So if I throw you half of a banana, the odds of it being the top is 50%. But when you catch it and you look at it and you find that it's the bottom of the banana, then what are the odds that the other person I tossed the other part of the banana to is the bottom half? 100%. It has to be, right? But if I'm tossing you a quantum banana where it's both up and it's both the bottom and the top half until you look at it, and then it becomes the bottom half, but I already tossed the other half to the other person, and they're really far apart, and let's say they checked it like almost right after the first person checked their half of the banana. So this half of the banana comes to the first person, they check it, and immediately, like within less than a second, the other person checks theirs. If they weren't determined from in the first place, but they have to be opposites, and by looking at it, it determined it to be the top half, then how did the other one know to become the bottom half? And they're saying for it to know that this one was checked and that it was the top, and therefore this one knows to collapse and become the bottom one, that it somehow some information must have traveled to that banana, and it would have to have traveled faster than the speed of light, and information can't travel faster than the speed of light. So that's, I think, the basic argument here. of why quantum mechanics doesn't make sense, according to Einstein.
Other photons had to travel faster than light to affect the other photon. EPR argued that since nothing can travel faster than light according to the rules of special relativity, this should invalidate the Copenhagen interpretation. This theorized violation is the EPR paradox. EPR proposed instead that there is likely another theory which would show that the two entangled photons were in cahoots from the very beginning, that their states were predetermined from their creation. In other words, their states contained the information locally so that when they were moved apart,
So the information about this one being spin up is already embedded within it. That's what he means by local. It's really already there. Whether it's expressed or not, it's somehow embedded within it. That's the idea. And that's where I guess the AI was saying Einstein believed in local realism, meaning it actually has the up spin in it encoded somehow, and the other one therefore has the down spin encoded in it. So when you're checking it, you're just revealing information that was somehow already there. It's not like you determined it somehow. Because for that to happen, the other one would have to know, oh, my partner is a spin up now. I guess I'm the spin down. I have to be according to conservation of momentum. But then how does it get that information? That's the issue. Not how does it get it, but how does it get it faster than the speed of light? Because you can set up the experiment so that the distance would require the information based on the duration between your measurements would have to imply that it'd have to get the information faster than the speed of light.
communication had to take place. The information that we were measuring was hidden inside the two particles. This is called local hidden variables. So for example, it's as if the two particles were a pair of gloves. One was a left-handed pair and the other was a right-handed pair. Once we found the left-handed pair, we knew immediately that the other pair, no matter where it was in the universe, must be a right-handed pair. This was a valid interpretation of quantum mechanics for almost 30 years. From 1935 to 1964, this could not be disproven. This is where Irish physicist John Bell comes in.
So I think he means it was a valid interpretation, meaning that there must have been some hidden variables there that are determining it, even though we just can't see it. Because I think that's the intuitive thought of like, oh, well, you can't observe it, but they're there somehow. And when you're observing it, the information is like, even if it doesn't seem to be in that state, then when you observe it, it becomes that state. Okay, fine. But somehow the information of what state to become was somehow present within it at some level.
In 1964, he proposed an experiment that could show whether the local hidden variable theory was correct or incorrect. Now, Bell's equation is remarkably simple, but it's one of the most difficult to understand and simplify. So I'll present a highly simplified idea of how it works, then also show you the simplified version of the mathematical underpinnings later in this video. Now we're going to play a game, and our opponent is going to be the universe. And the game is guess the color of the checkers pieces. Now I want to give a big shout out to Jim Al-Khalili, who shows a similar simplified illustration in a documentary available on Magellan TV. I encourage you to check it out because it's fascinating. If I guess the color correctly, I win. If I'm incorrect, the universe wins. In the first game,
If the universe wins, I also win, don't I? Oh.
I declare that if the colors match, I win. The universe picks the pieces. Now in play after play, I find that I lose every time. So in the next round, I change the rules. This time I declare that if the colors are different, I win. The universe picks the pieces. In play after play, I find that I lose every time again. So I conclude that perhaps the universe has rigged the game against me. This is what Einstein suspected was happening, that the checkers pieces were rigged. He believed that the colors of the pieces were predetermined, and that this information had been known from the very beginning when the two pieces were together. Niels Bohr's idea, on the other hand, was that the red and black don't even exist until the piece is turned over. So I changed the rules of the game again. This time I do not tell the universe whether matching colors or different colors will win the game until after the universe.
That's interesting. That's interesting. Okay, so he's not even going to say what the rules are until he can look at them?
Universe has
Oh
already.
no, once he selects them. Okay, because okay. If I say, all right, you get to choose the pieces, and I say if they match, I win. It's then the universe is going to be like, all right, well I get to choose the pieces, so I'm just going to choose ones that don't match, and I win. So this time he's like, well, that's because it's getting to choose the pieces, right? So I think that's what they're saying. So this time, choose the pieces first that you think will win, and then I will tell you the rule afterwards. Okay.
Already picked the checker pieces. If after revealing the checker piece,
Or in other words, it's not like, okay, you put them down and then I'll tell you the rule, so like you're cheating. It's more like you have to choose them first. You can't choose them after I tell you the rule. You have to choose them first. So now they're predetermined, right? That's the idea. Now they are predetermined. So you can't try to cheat the thing. Because if you keep playing this over and over, sometimes you would win and sometimes you would lose, right? Because the universe wouldn't be able to, I mean, I know it's the universe, whatever. This person wouldn't be able to guess every time. They would be like 50-50 probably, right? Like sometimes they would put out only matching ones. But you, that time, you determined the rule was going to be it's matching ones win. Sometimes they would put matching ones when you decided different colored ones would win, or non-matching ones would win. But the point is that they're predetermined, so they can't change it after it knows the rule.
I find that I win 50% of the time
Right.
and lose 50% of the time.
Right.
Then my conclusion is that indeed the checker pieces were rigged from the very beginning, because my chances of winning would be 50% if the red and black pieces were already picked by the universe.
That makes sense. Meaning, so if it's the case that it's choosing them up front, it's already chosen the pairs, it just hasn't revealed them to you, then if the rules are after you've chosen them, we just haven't seen them yet, if I then determine the rule, then I should win 50% of the time, round by round. 50% of the time I would win because clearly they're predetermined. Or so if they're predetermined, then that would be the conclusion, is that you would win 50% of the time. That makes sense.
But if I continue to lose, then I have to conclude that somehow,
Yeah, if you did that version of it and then you kept losing on average, you'd have to be like, how the hell is that happening? Like, in other words, what if you were playing the game and you kept losing even after you did that setup? Then you might have to conclude potentially, that's weird. Maybe the other player has some way of either cheating but not predetermining what the pieces are. Right? Like if they're actually not predetermined, and then only when the rule is applied is it determined, that would be why you would lose more. Just like in the first case when it was very obvious, you were telling them the rule before they chose them, so they're going to choose ones so that you lose. Okay.
the colors of the checker pieces were not chosen ahead of time. Let's look at how Bell's elegant equation proves my conclusion. To do this, let's look at a universe where local hidden variables are correct. In other words, entangled particles have predetermined properties which are complementary to each other at the moment of their creation. Note that this is not an interpretation of quantum mechanics, it's an alternative to quantum mechanics. So in this system, when two entangled particles are produced from a process that conserves linear and angular momentum, we will get two particles that go off in opposite directions, and they will have opposite spins as well as opposite directions. Let's say Alice makes the measurement on particle 1 in her laboratory, and Bob makes the measurement on particle 2 in his laboratory. And let's say the two labs are very far apart and are not in communication with each other. If Alice measures the particle spin in the z direction as positive, Bob will measure the spin as negative in the z direction.
So what would you expect? 50% of the time, she's going to measure the positive spin. Okay. And that would correspond to him. Okay, well, I'm going to let him keep going.
If they measure the spin in the x direction, which is orthogonal to the z direction, or 90 degrees apart, the same type of complementary opposite spins will be measured. Because as I said earlier, angular momentum is always conserved. What Bell's inequality does is it says, now let's make a third measurement that is somewhere in between the z and x axes. In our example, we use 45-degree angles to the z and x direction. We'll call this the q direction. So in a universe where local hidden variables are true, when the two particles are emitted, they know what their state is going to be in all three directions, z, x, and q from birth. And there are only 8 combinations or possibilities of spins that each particle could have. So for Alice and Bob, these 8 combinations will be the following. The event 1 could be where the spin in the z direction is positive, the spin in the x direction is positive, and the spin in the q direction is positive.
Okay.
E2 is when z is positive, x is positive, and q is negative. E3 is when z is positive, x is negative, and q is positive. E4 is when z is positive, x is negative, and q is negative. E5 is when z is negative, x is positive, and q is positive. E6, z is negative, x is positive, q is negative. E7, z is negative, x is negative, and q is positive. E8, z is negative, x is negative, and q is negative. Now let's ask the question, what is the probability that Alice measures in the z direction, gets a positive spin, and Bob measures in the x direction and gets a positive spin?
$25%?
Well, if the above case is for Alice, there are 4 events where z is positive.
Oh, I see. She measures that and he measures it. Okay. All right, yeah.
In order for Bob to get x positive, Alice would have to have measured x as negative. So these would be an event.
Oh, right. Okay. The second one is Bob getting the x positive. I was actually thinking it meant Alice, but that makes sense. Okay. So it's these two. It's E3 and E4. Did you say there's 8? Yeah, there's 8 of them. Okay, so
Events 3 and 4. To get the probability,
Yeah,
we have to divide by the total number of events, which is 8. Let's do this for 2 more scenarios. What is the probability that Alice measures positive in the z direction?
Oh, okay. This is making sense. The sock analogy was fucking not helpful at all. Because in this scenario, there's multiple things that can be measured. So, and they're not able to communicate with each other. So she's she's measuring the z, and he's measuring the q. So what are the odds that she would measure a z positive, and he would also measure an x positive, 1/4? Right? What are the odds she would measure a z positive and he would measure a q positive? I would assume also 1/4. Z positive. Yeah, I mean, obviously, right? Okay.
Direction, and Bob measures positive in the q direction. In this scenario, it would be event 2 and 4. Again, we divide by 8 to get the probability. And the third case is, what is the probability that Alice measures positive in the q direction and Bob measures positive in the x direction? This would be event 3 and 7, divided by 8 for probability. So these are the 3 probabilities given the hidden variables theory. Now here's the big insight that John Bell had. If I take the total number of events and multiply that by the probability that Alice measures z positive and Bob measures x positive, this has to be less than or equal to the total number of events times the probability that Alice measures z positive and Bob measures q positive, plus the probability that Alice measures q positive and Bob measures x positive.
Okay. There must be some math behind that. I don't quite understand why that would be the case, but wouldn't that just be, you could divide by 8, and then this would be 1/4 plus 1/4, which is 1/2. Okay, let's just see what he says.
When we write this out, the 8 cancels out and we are left with just the probabilities. This is Bell's inequality. Now I can prove this is true by doing simple math. E3 plus E4 divided by 8 is equal to E2 plus E4 plus E3 plus E7 divided by 8. The 8
I get that. How did you come up with the inequality?
8's cancel out, and we rearrange the order of addition, and we're left with this. E3 plus...
Okay. So assuming this inequality is true, which, I mean, maybe it's not that complicated. I'm just not seeing it easily. But let's assume that inequality is a fact. Then if you... I don't understand why he just dropped the probabilities, though.
E4 is less than or equal to E3 plus E4 plus E2 plus E7. This makes total sense because E3 and E4 are on both sides of the equation, and E2 and...
Okay, that makes sense. That would have to be less than that, because if you're adding some positive numbers to itself, it would have to be less than or equal to that, unless the other ones are 0. They can't be a negative probability. So either there's E2 and E7 are 0, or there's some positive number. So it makes sense that E3 plus E4 would have to be either equal to that, if those are both 0, because it would be equal to itself, or less than that, if either E2 or E7 are positive numbers. Then obviously it's like A has to be less than or equal to A plus B if B is not negative. That's obvious. Okay. I still don't understand how he just drops the probabilities, though. Maybe he's just saying it kind of like intuitively. But it makes sense if you were to work out the math of the probabilities.
E7 have to be positive. So this inequality absolutely...
Let's just go back to this part. The reason he drops the probabilities is so that he can rearrange the E3, E4, and all that. Okay.
E4 is less than or equal to E3 plus E4 plus E2 plus E7. This makes total sense because E3 and E4 are on both sides of the equation, and E2 and E7 have to be positive. So this inequality absolutely has to be true for any hidden variables theory to be true. Now remember, these probabilities are for a universe with hidden variables. But what happens in a universe where the laws of quantum mechanics are correct and not the hidden variables theory? Well, this inequality is violated in quantum mechanics. How is it violated? Let's say Alice measures the spin to be positive in the z direction. Then we know that if Bob measured the particle in the z direction, he would get a spin that is negative. However, Bob doesn't measure in the z direction, but in the q direction. What will the spin of this particle be? In hidden variables, there was a 50% chance that it would be positive and a 50% chance that it was negative. But this is not what happens in quantum mechanics because the measurement of the particle follows the probability laws of the wave function for a particle rotated 45 degrees. And that probability of Bob measuring Q to be positive after Alice has measured C to be positive, if the angle between them is 45 degrees, is given by the following equation. Sine squared of 45 degrees divided by 2. This comes from the math of quantum mechanics. This is the critical difference between quantum mechanics and hidden variables theory. The probability that Bob measures the same spin as Alice, depending on the difference in angle measured, is not linear, but looks like a sine wave. When you plot this out, this is what the probabilities look like. You can see from this graph that at 0 and multiples of 90 degrees, the two systems are in agreement. But in between, like at 45 degrees, the probability is 25% for hidden variables and about 14.6% for quantum mechanics. But the proof is in the pudding because in test after test, the sine function correlation has been confirmed. The particle does not behave linearly, and so the hidden variables theory cannot be correct. Bell's inequality is violated. So we can write out and compare Bell's inequality for both cases. For hidden variables, the equation would be E3 plus E4 is less than or equal to E3 plus E4 plus E2 plus E7. 2 is less than or equal to 4. The inequality holds true. For quantum mechanics, the equation would be sine squared of 90 degrees divided by 2 is less than or equal to the sine squared of 45 degrees divided by 2 plus the sine squared of 45 degrees divided by 2. And when you solve this, you get 0.5 is less than or equal to 0.293, which of course is not true. So Bell's inequality is violated in quantum mechanics, which is exactly what we observe in experiment after experiment. Now,
That's interesting.
does this prove that the two entangled particles are communicating faster than light? There is differing opinion on this. On the surface, it does appear that superluminal communications is taking place, but my personal opinion is that no communication is happening. The two particles are really just part of one wave function. And since the wave function can theoretically be as wide as the universe, when this one wave function collapses, both particles collapse. And since the collapse is random, it cannot be used to communicate in this way. So most theorists do not think special relativity is violated because we can't communicate using the seemingly faster than light phenomenon. But our knowledge of quantum mechanics and entanglement is incomplete to say the least. Why is there superposition? What is the mechanism of wave collapse between two particles separated by space and time? I happen to think that the scientist who's going to reveal the mystery of quantum mechanics is alive right now in the world, and I can't wait for him or her to explain this and, like Copernicus, Newton, and Einstein, completely change our paradigm. I'll see you in the next video, my friend.
That is really interesting. That is really interesting. So according to that, if you make the assumptions that there are hidden variables, then you would get these probabilities of different measurements being made, and therefore you could form a certain inequality, and that inequality would have to be true. But according to the mathematics of quantum mechanics, the probabilities would be different, and it would violate the inequality. And it turns out experimentally, apparently anyways, the inequality is consistently violated, which would imply that there aren't hidden variables, which would imply that either it's information is traveling faster than the speed of light, or that's not happening, and literally the particles don't have any hidden variables, and the particles are not actually even physically separate at all. They're literally a wave, and so when you're collapsing it here and you're observing it, it's simultaneously collapsing here because it's all the same thing. Damn. And I didn't even get that far tonight. I'll give you a preview of what I want to talk about tomorrow, because I don't want to. We're going to go another 2 hours if I go into everything else. Let me show you where I want to take this. Doug Huffman, is that right? The Grand Transdimensional Delusion. Definitely not what I was looking for. Donald Hoffman? Hoffman? Doug Hoffman? Yeah. Here's the guy. Let me see if I can give you a little preview real quick. Where's my... Is it Doug? Oh, it's Donald. Donald Hoffman. Why can't information travel faster than the speed of light? Oh boy. We'll save that question for tomorrow. We will address that question tomorrow. But I'll give you a little quick preview about where we're going with all of this. Okay, let me see if I can find one that kind of gives you a little quick hit. Where's the one I'm looking for? Where's the one I'm looking for? Where is the one I'm looking for? Hold on. It'll be worth it, trust me. I think I have it in my other browser. Let me double check. Let me see. This one. Copy link address. Okay, I'll give you a little preview for tomorrow, and we'll talk about the speed of light stuff too.
So it's a small, but those who have studied it. So
stop. Okay, that was crazy. Let me see. Here's the highlights. We'll just watch the highlights real quick.
you can ask, well, how in the world can you think outside of space-time? How can you even think outside of space-time? But you can. Once you start to do it, you get the hang of it. Oh yeah, okay. You can think about the amplitude-hedron as a geometric object. It's outside of space-time entirely. You could have trillions of dimensions. Space-time only has 4, maybe 11 if you're a string theory. The amplitude-hedron can have trillions or quadrillions, untold numbers of dimensions and vertices and so forth. So this really complicated object outside of space-time, and it's the volumes. The volume of the amplitude-hedron turns out to code for the probability, or what they call the amplitude of particle interaction. So like at the Large Hadron Collider, like, 2 quarks smashing into each other and 4 quarks, or quarks coming out, or more likely 2 gluons and 4 gluons spraying out. What's the probability of that kind of scattering event? And so it's coded for in the volumes of the amplitude-hedron. And what's interesting is that it's a geometric object. It's not a polytope, but it's like a polytope. It's got facets and edges and vertices and so forth, right, and then faces of different dimensions. And it turns out when you look at the whole structure of all the faces and the edges and so forth, that structure itself codes for locality and unitarity, space-time, and properties of space-time and quantum theory. So it's interesting. It's a geometric object. It's static. It's just sitting there. It's this monolith beyond space-time. Its volumes are the scattering probabilities or amplitudes, and its geometric structure codes for locality and properties of space-time. And then behind the amplitude-hedron, even deeper, they found these things called decorated permutations, right, which are the deepest core somehow from which the amplitude-hedron gets its structure, that codes for these properties of objects in space-time. So but these just, there's no dynamics now. We've let go of space-time. We've taken our first baby steps into the realm beyond space-time, and what we see are these monoliths. They're just sitting there, pregnant with meaning, but no dynamics. So we're very much like 2001: A Space Odyssey, where there's the monolith there, and there's the apes. Yeah. They see it, they're first scared of it, and then they pound on it, and they're screaming at it, and they're jumping all. Yeah. They know that it's something important, but they're clueless, and we're sort of in that same. We found these wonderful monoliths, but who ordered that, and why? Why the amplitude-hedron, and why aren't we seeing no dynamics? It's just these rocks, these geometric objects beyond space-time. Sure. You're absolutely knocking on the right doors here, and I've been trying to knock on.
Okay, so none of that probably made sense, but here's the teaser, right? What some modern physicists who are doing really advanced research are coming to the conclusion of is that even what we call space-time isn't a fundamental property of reality. Even quantum mechanics are not fundamental properties. Even the particles that they're talking about with quantum mechanics and particle physics are not fundamental at all. And these are things that are emerging from something else. There's something else, they're calling it the amplitude-hedron, and then behind that it's called the decorated permutations. And this is like Princeton researchers. This isn't just some like woohoo, woo woo out there like crazy spiritual bullshit. Not that I'm saying it's valid necessarily. I'm just saying this is like mainstream physics research. Okay, MIT, Princeton, that kind of stuff, and some very specified researchers, and they're coming to the conclusion, anyways, that even what we call space time is a emergent property from something even more fundamental. So even all the theories of Einstein, even all the theories of quantum mechanics, the reason why, and we didn't really go into it yet, maybe we're not going to be able to jump straight to this tomorrow night. Maybe we won't even get to it. Maybe we'll have to keep going a little bit and diving deeper. But that's ultimately where we're going with it, okay? Is that there's a conflict between quantum mechanics and relativity. Okay, and so someone asked in the chat about, why is it that information can't travel faster than the speed of light? Because like you hear this, but the question is like, why is it? So perhaps tomorrow we'll kind of start with that and look at what is relativity theory, because we're really just like scratching the surface here, and obviously we're going to be limited by the fact that we can't do all of the math and everything. And there was a little bit of math in the last video, but it wasn't too crazy. But there's a lot of really complex specific math that we're not going to be able to do. So we'll do our best to kind of get the analogy versions of things and discuss it that way. And we're kind of looking more at like the conclusions and then the different interpretations and so forth. But the bigger point is when we go into relativity, we'll start to see that there's certain implications that don't make sense if quantum mechanics is correct. And there's like something that can't be reconciled. And so that's why Einstein was looking for a unified theory, and people have looked for unified theory, something that unifies. In other words, scientists basically are confident they can observe things that are consistent with what quantum mechanics predicts. They can observe these things in reality. They can also observe in reality things that are consistent with what relativity theory suggests. And yet, these two things don't agree with each other. Okay, and I'll give you another little teaser, and I'll probably have to find something to explain this further, but I was reading something saying that the amount of light that you need, the frequency, the energy of the light that you would need to be able to look directly at a photon, or any particle for that matter, has so much energy, it would create so much mass locally in that little tiny area that for that size, it passes the Schwarzschild radius, which would create a black hole. So in other words, when you try to use enough energy to really get really fine-tuned and see very closely at the smallest possible length, the smallest possible distance in reality, there's so much energy compacted into that tiny little area that it creates a micro black hole. And a black hole is something that the gravity is so dense, light cannot escape it. In other words, information cannot escape out of it. So it's like you literally can't see beyond that point. No information can come out of it, right? Which sounds kind of wild and wacky, I understand. But don't blame me if it sounds wild and wacky. It's not my theory. I'm telling you what modern physicists say. So when you hear all these, like, you probably heard like, oh, they're going to open up a black hole at the Hadron Collider and all, like, that's where I think a lot of those weird little rumor type things come from, is from actual physics and some of their conclusions. I don't think it means they're literally going to open up a wormhole that's going to suck everything into it. I think it's sort of an exaggeration of the point. But it also comes from not understanding what a black hole means, like what a singularity means. So, man, there's so many different things we can talk about. And I think I'll just keep going into this rabbit hole until we get either exhausted by it or overwhelmed or perhaps bored with it. And then we'll find something else more interesting to talk about. But again, I have a long-term vision for what I want to do with this stream in terms of what I want people to understand. And what I'm trying to do right now is just build a very clear picture to people, especially with this kind of stuff we're talking about now, is build a clear picture for people that if I were to say something that sounds out there, okay, which I will eventually do if I haven't already, just because something sounds out there doesn't mean it is. Like if I said, oh, they're going to create a black hole at the Large Hadron Collider, it sounds out there. But then if you go look at the actual math and the physics and what the scientists are saying, you're like, oh, I see why they're saying that. In other words, something can sound out there because you really don't know much about things. So even just what I demonstrated earlier in tonight's stream, when we were talking about the Bohr model and the Bohr-Rutherford model, the Thomson model, and all these things. What was the other one? It was Bohr, and then there was the quantum mechanical model. And then you realize, like, oh shit, man, I spent 12 years in school and I didn't even learn anything past the 1920s in physics. Like the 1920s, 30s. They didn't even have cell phones, or like they didn't have computers back then. And why is it that I wasn't even exposed to anything beyond that? And then even if you get a physics degree, and probably even if you get a master's or a PhD in some cases, you don't even get exposed to the cutting edge. It's like there's very few researchers who are doing research on the cutting edge. And I'm not saying that implies they're finding the truth, but they're trying to go beyond what the current theories are. So you just start to see like how limited everybody's education and vocabulary is around certain topics. So that way, the problem being when you bring up other ideas, somebody might be like, well, that doesn't sound realistic, right? But do you even understand quantum mechanics? Do you even understand any physics past the turn of the century? You know, or well, the last turn, not the last one, the one before this past one. Everybody has been so dumbed down. And I really don't think it's beyond the capacity of people to really understand this stuff. Yes, there are people who are like kind of super geniuses who can like hold a lot of information in their mind. And I understand that. But at the end of the day, if they're the only ones who understand it, that's not really helpful, is it? And if they're going to use their theories to draw conclusions and then apply those in reality and that affects our life, shouldn't we kind of know if we can trust that or not? Right? So everybody has been so dumbed down by an education system. And that's why I was kind of showing earlier with my kids. It's like they're out there like looking at plants, like they're like 4, 7, and 9. Like they're teaching themselves piano. They're looking up plants. Like my children are reading like sci-fi, like novels, like all kinds of stuff. And they're doing this on their own, but it's because they're getting support from us with their education in terms of their vocabulary and so forth, and their reading abilities and their math abilities. And so what humans are actually capable of is so much more than we realize, because we've been normalized, or a certain level of what we think the average human is capable of has become normalized, and it's actually a much weaker version than what people could be if they were supported effectively, right? The education system has done a number on most people, even to the point where learning just seems like difficult and boring. And like, I mean, I find this stuff fascinating, you know, like reading all these books, listening to all these things. And yes, there's limitations, because if you can't do all of the advanced math, then you're limited. But then you're like, okay, well, what if I really did want to understand this? What would I have to learn? Okay, let me go back to where I stopped learning math, and let me see what math is required for this, and let me just learn it. And that might take time, but then you have to ask yourself, is it worth my time? And is this important for me to know or understand or be able to verify or whatever? So obviously doing a stream, we can't do all that because you have different people at different math understanding and knowledge and so forth. There's even gaps in my knowledge in terms of all this advanced physics stuff. So we're going to have to work with the fact of, okay, we're looking at people's conclusions. And sometimes some of these guys are really good at communicating, like, okay, here's the conclusions I've come up with. And that's what we're interested in. So anyways, just kind of a general idea of where I'm going with this. So for tomorrow night, I think we'll look at some relativity stuff, because I think that'll be really interesting. It's like kind of mind-blowing stuff because it's so counterintuitive completely. So with quantum mechanics, you've got this idea that things don't really exist in a certain place until you observe it. That's weird. Well, relativity theory has its own very weird stuff, and I won't spoil it. We'll get into that tomorrow night. And then depending on how far we get with that, then we can see, can we put some things together and go a little further? Because let me see if I can give you a simple point with this guy, that Donald Hoffman. Now, he's not the guy who's originating some of these theories. He does have some theories, but he's discussing the work of this physicist, Nima Arkani Hamed, and other things. And, well, I'm not even going to spoil it. You'll have to just be there and see where we go with it tomorrow night. But we'll start with relativity theory and see how far we can get with that. Okay, everybody. I'm going to leave it there for tonight, and I will see y'all tomorrow night, 8:30 p.m., same place. Have a good night, and I'll see you tomorrow.